So we'll see how close you get to your drawings. The 1-bromo-2-methyl cyclopentane should look this. You may have your bromo over here. You may have put it here, as long as you have a 5-structured carbon in a circle with a methyl group and a bromo group attached, like on 2 carbons that are next to each other. And the 1,1-dichloryl-3-ethyl cyclohexane looks like this, 1,1-dichloryl. You could have put that at any location, as long as 2 carbons away from it, you have an ethyl group. Now, an ethyl group, you may have drawn it out like that, indicating carbon-carbon, or you may have put the condensed formula, or you may have gotten wild and crazy and with all of these and have drawn actual C's. And all of the H's, except on this one we would have a C and a C and an H and an H, H, 2 H's on each of those. Did any of you get wild and crazy and do that? There's really not a need to get wild and crazy and do that if you don't need to. Okay. And that is the end of this slideshow. So now we'll talk a little bit about alkenes, and then we'll build some stuff. And I want to thank you guys again for being able to stay later on these 2 days to make up for the other days. The slideshow is shorter. So again, this is from the textbook itself, and some of the slideshows that I'll use in this class are from there. Some of them I've taken bits and pieces from different places, from other instructors, and pieced them all together. So what we have each week might not always have exactly the same face. Some new things that will come about with alkenes, which I shouldn't have said alkenes. This topic is unsaturated hydrocarbons, which may contain 1 or more double bonds, which are alkenes, or 1 or more triple bonds, which are alkynes. So we'll start talking about alkenes. And then we're going to learn something called geometric isomerism, and that's something that's a bit new, that occurs only when you have double bonds. And then talking about cycloalkanes, which can also occur, a little bit about alkynes. Then we have a category of compounds called the aromatic hydrocarbons, how to name them, and I don't know if I have this stuff in there or not. We'll have to wait and see. I might have gotten rid of some of that. So some of the uses for our unsaturated hydrocarbons, they make our plastic bags and our bottles, styrofoam, plastic wraps, a lot of cosmetics, medicines, flavorings, perfumes, detergents, insecticides, and dyes. The alkanes are mostly restricted to use as a fuel source or an energy source. So the unsaturated hydrocarbons, a little more versatile, a little more useful to us. And we have the alkenes, which contain that carbon-to-carbon double bond, at least 1 or more. The alkynes contain that carbon-to-carbon triple bond. And then the aromatic compound contains this right here, which is that benzene ring. And I just want to remind you that you may also see this drawn like that. And what they've discovered with the benzene ring is that, like, if you look at between these two carbons, we can say two electrons or two pairs of electrons are being shared. So we have like 4 electrons between these two carbons. And we have 6 total electrons between these two carbons. Now it would seem that we would have 4 here, 2 there, 4 here, 2 there, 4 here, and 2 there. But what ends up happening is that it appears that all of these electrons get shared equally around this entire structure, and they call them delocalized electrons, meaning they're not, the electrons that are being shared are not specific to the bond between these two carbons, so they're referred to as delocalized electrons, and that's why sometimes you'll see the benzene drawn as that 6th carbon with this circle, reminding us that the electrons that are being shared are really kind of being distributed around that entire ring structure, which we'll talk more about that when we talk about those aromatics. So alkenes are very similar to alkanes. The first thing that you have to do is find that longest chain. Now this can be tricky, especially if anyone's trying to trick you. Sometimes when you have those chains going like this, that's exaggerating a lot, but sometimes they can be tricky. So we have to find the longest chain. The ending changes a little bit. This 3-carbon chain, this is an alkane, and we call this propane. In this case, because it's an alkene, we call it propene. Now, for any alkene with more than 3 carbons, we have to do a little something extra. And the next slide shows this. So here it says number the carbon chain to give the double bonded carbons the lowest numbers. So here you can see that we've got 4 carbons, and this double bond is in between the 1st and 2nd carbon. Since we have 4 carbons, this would be a butene. We have to call this 1-butene. So you have to remember to start counting from the right side. 1, 2, 3, 4. We wouldn't call it 4-butene or 3-butene because that is too high of a number. With this one, the double bond is on the 2nd carbon, so we call it 2-butene. Now, the reason we only have to worry about this for carbon chains that are 4 or higher is because with that 1 carbon chain, there's only one possibility. That double bond is going to be between the 1st and 2nd carbons. So you generally won't see us say 1-propene because there is no other option. But when you have 4 or more, that double bond can be in more than one place. Now, naming the groups is very similar, except this time, what determines the direction that we number from is the location of the double bond. So, for example, if we're looking at these, if this was just a regular old alkane with all single bonds, we would start numbering from this end because this methyl group was closer to this end. In this case, we have to start numbering whichever number will give us the lowest number for the placement of the double bond. So this is a 1, 2, 3, 4, so it's a 1-butene, and if this is 1, this has to be 3, that makes it 3-methyl 1-butene. Here we have a 1, 2, 3, 4, 5, 6, a hexene with the alkene group on that first carbon, and attached to the third carbon is a 1, 2, a 3 carboned alkyl group, which, remember, 3 has to do with propane, so that's called propyl, 3-propyl hexene. So again, it's very rare that you see groups attached that have more than 3 carbons. We will come across them, but it is quite rare. Okay, so here it says, what is the structural formula of 4-methyl-2-pentene? Okay, so working backwards and thinking this through, I have pentene, 1, 2, 3, 4, 5. It says 2-pentene, so I know my double bond must be on the second carbon, and it says 4-methyl. So if this is the second, 1, 2, 3, 4, 4-methyl, a methyl group has 1 carbon. Now, I'm just going to put all of the hydrogens on here. Remember, every single carbon should have a total of 8 electrons around it, which is the equivalent of 4 bonds. 2, 4, 6, 8. 2, 4, 6, 8. Wherever you have a double bond, you're going to have fewer hydrogens. That's why these are called unsaturated hydrocarbons, because there are fewer hydrogens. Now, I am just going to put them right there because I have this one going in the up direction. This carbon has 2, 4, 6, 8 around it, as does this one, 2, 4, 6, 8. This carbon only has 3, so we're going to have a hydrogen there, a hydrogen there, a hydrogen there, and a hydrogen there. Now, we could draw this a variety of different ways, and I feel like I should probably do that. So if I make a condensed structural formula, there are a couple of ways I can do it. I'll show you both ways. We have CH3, CH. Sometimes that double bond will get put in there. CH, CH. Because I've gone in that direction before and I don't have a lot of room there, I'm just going to bring it down. It's the same thing, CH3, CH3. Now, I did not mean to put that dash there. I meant to draw them all together, only showing the double bond. You could put all of the bonds in, CH3, CH, 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 CH3, CH3. This is not as common. And even more common than this would be to leave that double bond out of there. CH3, CH, CH. CH, CH3, CH3. Now this gets a little bit confusing, I think. CH, 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 it sounds like a choo-choo train. But this is another way showing that condensed formula. I personally like this one because it's immediately obvious to us. Now remember, I would have this a little bit closer, but it's immediately obvious to us 2 things. One thing is that there's a branch in there with the methyl group, and another is that this is a substance with a double bond. So I particularly like that because you can see the double bond. We can turn this into a line structure. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now with a line structure, in between the second and third carbon, there's a double bond, and it looks like that. On the fourth carbon, there is a methyl group, which looks like that. One thing you will always see when we do these line structures is that if groups are attached, you'll always see them coming, like going towards where the peak is. So I would never have drawn this like with a group coming down like that. It's just kind of awkward. So if the methyl group is on this a tippy top peak, I would go up with it. If the methyl group were, if I were to continue this, on this carbon, I wouldn't go up with it, I would come down with it. So that's just kind of a methodology for doing that. Now let's see what they did. I just wanted to remind us of all of the different ways we can represent things. So it looks like they drew kind of the ziggy-zaggy line structure with the carbons, and it was a kind of combination of all of them. So 5 carbons in the longest bond, the double bond is between the second and third carbons, and you see the methyl group on 4. All right, what is the name of this? I'll let you guys try. I want to remind you that you do need to find the longest carbon chain. What I didn't emphasize before is that it has to be the longest carbon chain containing the double bond. So it's very tempting to start doing this, right? But that longest carbon chain, if there is a double bond within a carbon chain there, that longest carbon chain must contain the double bond. So we can either go this way, which is not, which means that we have to go this way as our longest carbon chain. Yep.
As we name these, and it's kind of like all scribbled out, like just start put one on the right, and numbers, and there's dashes, and then sometimes they'll put like group, but it really should all be combined. Like, would that ever be an issue?
With me, no.
Yeah.
No. Where it might be an issue is if you were to take it, and this is so annoying because I've done it, if you were to take it upon yourself to go online and try to do tutorials or quizzes, interactive types of things where they have you naming these things, if you end up putting a comma or a space in the wrong place, it'll keep telling you wrong answer, wrong answer, wrong answer, and then you find out the right answer is essentially what you put, and it's so frustrating. I will never try to trick you deliberately into having something so, like, to put one with a dash in one spot and not a dash in the other. Or if you're drawing out, if you're writing out the name and you don't put a dash when you should have, or don't include a comma where you should have, I don't let those sorts of things bother me at all. Because, I mean, it's a lot, for sure. That's a really good question. Sometimes you may see me inconsistently do things. I try to be as consistent as I can, but it happens. So we have our longest chain is a 5 carbon. So our 5 carbon, oh, my little diagram kind of switched spots. I thought it was going to stay in the same spot. So here's our longest chain, it's a 5 carbon, and between the first and second carbon is that double bond, so it's going to be a 1 pentene. And on the second carbon, we have a group attached with 2 carbons, which makes it ethyl. So 2 ethyl, 1 pentene. Okay. So with there's something called geometric isomers. Now, geometric isomers occur around this double bond. And what we're looking at is, I particularly like to look at where the hydrogens are located. In this one, the hydrogens are located on the same side as the double bond. And when that occurs, it's called a cis isomers, a cis isomer. So, excuse me. With the name here, let's break this down. We have chloro, so we have 2 chloral groups. We have a 2 carbon chain, 1, 2, which is ethene. I don't think it was necessary to say 1, 2 dichloroethene, but actually it is, you do need to say 1, 2 dichloroethene, because you could have put the chlorine here and the hydrogen there. So that would be 1, 1 dichloroethene. Now I need to erase that because that's not what it is. Okay, so I spoke too soon there. But if you look at the double bond where the hydrogens are on the same side, it's called a cis isomer arrangement. Where the hydrogens are on the opposite side, now I like to think of this as, it's called trans, I like to think of a transatlantic flight. So they're over and beyond, away from each other. That's called a trans isomer arrangement. They're both 1, 2 dichloroethene. But if you notice, the difference between having those hydrogens on the same side and the chlorines on the same side versus the alternative, the properties of this substance changes just with that little bit of a flip. The boiling point of this is 60 degrees Celsius, the boiling point of that is 48. So a tiny little difference changes the properties of it. This is one thing that the pharmaceutical industry uses to its advantage from time to time. It will have a drug, an established drug that works well. And it will make a similar drug, but one portion of the molecule, they manipulate it so that there's just a little bit of a change. Now with a really huge molecule, that little tiny change isn't enough to really change the properties. So it behaves in the body the same way. So what drug companies do is they make a drug. Do you guys know how long it takes for a patent to run out on pharmaceutical drugs before you can start making a generic? It's 10 years. I don't know if legislation has changed, but so this new drug comes out. The company has the patent of that drug for 10 years, so a generic drug cannot be made. It's considered one of those higher tiers. They get more money for it. There's usually higher co-pays when you don't have a generic alternative. So after 10 years, that runs out, and these companies can start making a generic variety of it. Well, all of a sudden, same company has this next new and greatest thing. They call it something else, because it has a slight, little tiny change in the molecule, which behaves exactly the same way in the body. Here you see the properties are different. But when you're talking a big, big molecule, just a tiny little portion, sometimes it could make a great change, sometimes not. But if it behaves in the body the same way, they'll market it as a new drug. They'll go and, as pharmaceutical reps, go and talk to the doctors and say, this is the next greatest thing, this is what you should be prescribing. And it continues money in their pocket. And why do the doctors prescribe it? because they're getting kickbacks too. So the pharmaceutical reps say, if you fill this quota, if you prescribe this drug, this many times this month, we'll give you this much of a bonus. So doctors have incentives to prescribe certain drugs. Now, I think that many doctors are very ethical in knowing how doing that can incur costs on their patients, and they're very good about it. If they want to prescribe it, oftentimes they'll have samples on hand and say, here's the samples, you don't have to go buy them. A lot of doctors will be like that. But it's a money racket. A lot of doctors can make money by prescribing that next thing. So let's see where this takes us. So alkenes with the same substances on the same side will be cis. So on the same side of the double bond is cis, and on opposite sides will be a trans arrangement. You've heard of trans fats. Trans fats are fat molecules, are very, very long chains of carbons made of fatty acids. They have unsaturated fats, just like unsaturated hydrocarbons have double bonds in them. If it's a trans fat, nature makes its fatty acids in a cis arrangement. When companies take those unsaturated oils, which are your vegetable oils like corn oil, soybean oil, vegetable oils, they take it and they have it undergo a process called partial hydrogenation. What ends up happening is these bonds end up switching. So here I have my hydrogens on the same side as the double bond. What happens is the molecule itself flips like this. And all of a sudden you have trans, and these trans fats have been shown to cause higher incidences of heart disease, high cholesterol, all of the things that butter used to get a bad rap for. And there's indication now that those hydrogenated oils, like a lot of your margarines and Crisco's and stuff like that, are actually worse for you than actually eating butter. So, if you have two groups that are the same on one side or the other of the double bond, then you will not get that cis-trans isomerism. Because if we're looking at, like here, if we're looking at hydrogens here around this double bond, there's no way to tell if, because these two are on the same side, but these two are on the opposite side. So the arrangement isn't the same. It's usually pretty obvious. So draw the chemical structure of cis 5-chloro 2-hexene. The structure that they're drawing on there is kind of intense, but I'm just going to keep this as basic and simple as I can. So hexene, we have 6 carbons, and it's 2-hexene. So my bond there is on that second carbon between the second and third. 5-chloro, 1, 2, 3, 4, 5. So we have a chloral group there. Now it says cis 5-chloro 2-hexene. It just means that I'm going to put the hydrogens right on the same side as the double bond. So if I just simplify this, I have CH3, CH, CH, CH2, CH. I'm going to put the branch to the Cl up there. There may be another way that you could represent it, and CH3. Now, looking at this, the way that I've drawn this does not really represent cis, because by looking at this, you cannot really tell which side is which. So if I were doing this, I would literally have to draw this out showing those hydrogens like that in order for that to be cis. Now, the way that they do it here, they do this ziggity-zaggityness. And there's really not an intuitive way to show this. But in a carbon chain, wherever you have a double bond in a cis arrangement, the carbon chain kind of wraps around like this, with the hydrogens coming out like that. Today when we build it, I'm hoping that arrangement becomes more obvious to you. If this were to continue on as trans, here I'll draw the same molecule in a trans way. It would be drawn like this. Instead of the C coming up like that, the CH3 would come down like that, and you would see the hydrogen like that. So what this results in really is more of a straight chain of carbons, a zigzag, 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 zig. So you'll see trans arrangements looking like this, but you'll see cis arrangements kind of looking like that. And I'm really drawing this bad, but wherever that double bond is, if you have this wrapping around like this, that tends to be your cis. And if you don't have that wrapping, then you have a trans. And we're going to build some molecules that show that better. I feel like I really just screwed up all of my drawings here. So whenever you have cis arrangements, you have molecules that curve more and curl around compared to trans, which end up being straighter.